Evaluating a movable palm in caging-inspired grasping using a reinforcement learning-based approach. This work evaluates robotic grasping whilst using a movable palm in the gripper. So, what are the benefits of using a palm for robotic grasping? This video shows a movable suction cup in the palm of a robotic gripper. Once a suction grasp is established, the moving palm pulls the object into the grasp so that it can be secured by the fingers. A movable palm can adjust its position to align objects of different sizes with the fingers. These figures show a suction cup palm and a granular jamming palm being used to help secure objects during in-hand manipulation. Both use negative pressure to lift objects, making it easier for the fingers to reposition during grasp. Finally, a movable palm also provides an additional constraint during grasp. Here is another in-hand manipulation example. Rather than use negative pressure, gravity holds the object against this palm whilst the fingers are repositioned. Movable palms have one key limitation. Since they move out of the gripper, they can push objects out of grasp. This is why negative pressure and gravity are used. They can provide a force pulling objects back into grasp and prevent this issue. However, previous work has not considered whether a rigid movable palm applying force away from grasp can actually improve grasping. Therefore, the present work answers two important questions. Can a rigid movable palm improve grasp success rate, and can it improve grasp stability? We made use of a method presented in our previous work, which trained a grasping controller using reinforcement learning. The controller was trained in simulation, learning to grasp using the gripper design that we presented. It learns to leverage a caging-inspired grasping approach, which surrounds objects, making use of the additional constraint from the movable palm. The gripper fingers are compliant, able to bend and adapt to objects, and provide a compliant opposition to the force applied by the palm. Then the finger bending and palm forces are measured and used by the reinforcement learning agent to select its next action. As shown, this method transferred well to a real prototype, achieving 98% grasp success rate in the real world. Therefore, the current work applies the training method from the previous work in order to perform a design study. We analysed how the movable palm affected grasp success rate and grasp stability. However, the movable palm, which applied a force away from grasp, required the gripper fingers to provide an opposing force, which would then keep objects in grasp. The opposing force provided by the fingers was dependent on two things, the finger stiffness and the fingertip angle. Hence, we applied the reinforcement learning training to 24 different design permutations to capture the effect of all these factors. We varied between two palm conditions, using the palm and not using the palm. Since the fingers can oppose the palm by bending, we varied between three different finger stiffnesses, each approximately 20% apart in terms of stiffness. Since the fingertip angle also affects how the fingers provide opposition to the palm, we varied fingertip angles between 45 degrees and 90 degrees, which is perpendicular. The 24 design permutations were then made up of every unique combination of these features. So, we trained grasping controllers for each of the 24 design conditions using reinforcement learning. The aim was to optimize grasping in every case, in order to form the basis for fair comparison of how each design condition affected grasp success rate and grasp stability. Each set of design features, for example, having 45-degree fingertips and not using the palm, was set in the simulation. Then, 10 grasping controllers were trained using each design, and the best was selected for real-world testing. Shown on the slide are grasps which did not use the palm across the 4 fingertip angles. Here are the same 4 fingertip angles but now using the palm. The images show grasps achieved by the controllers trained for each of these designs. Finally, each single condition on screen was repeated 3 times, every time with the 3 different finger stiffnesses. That resulted in finally 24 design permutations. This video shows a grasp being completed, on the left using the palm and on the right not using the palm. Grasps were tested to determine how successful controllers were, and then successful grasps were probed as shown to determine their stability. A probe rig pushes the grasp, measuring the force that it can tolerate. The experiments measured 4 aspects of grasping. Firstly, whether grasps were successful, which meant the object was lifted and all contact forces remained below 3 newtons. 2 examples are shown here. Top shows a grasp of an object which is caged by the design, which means the object cannot escape without pushing aside one of the fingers. The below image shows a grasp of an object which has not been completely caged. Here the Pringles can, which is not blocked from escaping grasp along its long axis. Next, we measured grasp tolerance to a disturbance in the most stable horizontal axis, which we termed the x-axis. This axis pushed directly against one gripper finger. We also measured the force each grasp could tolerate in the least stable horizontal axis, termed the y-axis. This axis pushes the object between 2 gripper fingers. For objects which cannot be caged, this disturbance corresponds to the axis along which the object is not caged. So for the Pringles can, it is pushing it out of grasp along its long axis. Finally, we measure the vertical disturbance tolerance, using the palm itself to push the object downwards. This would be analogous to increasing the weight of objects and determining at what point they fell out of grasp. We tested on the 18 YCB food objects, which are from a standard benchmark set. During testing, each object was placed beneath the gripper subject to position and orientation noise. Then, a grasp was attempted by the reinforcement learned controller. Each attempt was limited to 250 actions and marked as a failure if the object rolled away, fell out of grasp, or otherwise became ungraspable. If the grasp was successful, stability was then tested in one of the 3 disturbance directions. Once all 3 directions had been tested for that object, we moved on to the next object. However, if the grasp failed, another attempt was made up to a maximum of 5 failures. As a result, each object had 3 to 7 trials, and the actual average was 4.1 per object during the experiments. This experimental procedure was repeated for each of the 24 design permutations, for a total of 1,752 grasps. Did the palm improve grasp success rate? This graph shows grasping without the palm in blue and with the palm in red. Simulation is shown with cross-hatched bars and real-world tests with solid bars. Each bar is the average of 3 finger stiffness trials. The range of these 3 stiffnesses is shown atop each bar. The highest real-world success rate was with the palm using the 75-degree fingertip angle. The next best performing fingertip angle was 60 degrees, where success rates with the palm were only marginally better than success rates without the palm. So, did the palm improve grasp success rates? Yes. The palm improved grasp success rate for every fingertip angle in both the simulation and real-world experiments. Did the palm improve grasp stability? This graph shows the stability of grasps in each of the X, Y, and Z disturbance directions, and for each of the 4 fingertip angles. Once again, each bar is the average of 3 finger stiffnesses, and the range is shown atop each bar. These results have greater variance, but the overall trend was clear as well as statistically significant. The biggest improvement can be seen in the tolerance to the Y disturbance, and on average, the palm did improve grasp stability for every disturbance direction and for every fingertip angle. The results can be summarized by 2 tables. Firstly, the results averaged from all 24 design permutations and grouped into those that did and did not use the palm. These averaged results show how the palm improved success rate and disturbance tolerance. Second, the maximum results, showing here the best case with and without the palm. Again, using the palm improved performance across all metrics. Overall, the average improvements were at least 7% over all the metrics, with the greatest improvement in Y disturbance stability by 28%. The best overall grasping success rate was from using the palm, reaching 96% over the YCB grocery object set. Now for a brief discussion of the results. The key result was that the palm improved grasping in all metrics. Success rate improved because the palm provided an additional constraint and more stable grasps which failed less. It also added another force sensor, leading to better quality learning in simulation because the reinforcement learning agent had access to an additional force measurement. The largest improvement in grasp stability was in the y-axis because the palm added friction to stabilize objects which could not be caged. This work also has limitations. The learning-based approach had only a 3% average sim-to-real gap for the 60 and 75-degree fingertips, but this widened to an 18% gap with the other two fingertip angles. This shows that transfer can be brittle and that real-world evaluation was essential. The palm improved tolerance to the maximum Z disturbance force, but it did so by also exerting an initial force. When this initial force was subtracted, the palm actually led to a 16% reduction in stability. Therefore, using the palm may struggle with grasping heavy objects. Thank you very much for listening.